if we are given two sets of data, we can plot them with a scatter plot. This is one of the one example. All the data sets are plotted with this blue dot. We can see from this scatter plot that the form is linear, like this, and the direction is negative. That's because of the slope of the straight line is negative. But we want to know if there are really relationship or how strong the relationship is between the x data and the y data. So this is the purpose for today's topic. And recall before we discussed the concept of the z-score. The z-score for a one-dimensional data is defined by z equals x minus mu divided by the standard deviation, sigma. In this scatter plot, we have two sets of data. The first set is x. For example, for this point, the x value is around 34. And this value of x is around 34.5. And this one is around 36 and something. So we have all this data for the x values. And for the y value, for example, for this pair, the y value equals around 156. And this one is around 148. And again, we have a set of data for the y values. We try to calculate the z-scores. We can calculate the z-scores for each x value. For example, for the first point, we said this is point 1, point 1. And point 1 here. The corresponding x value is x1, the corresponding y value is y1. For the x1, we use zx1, the z-score for the first point in the x direction is the x value here, x1, this value, and minus the mu x. Mu x is the mean of all the x values, and divided by sigma x. Sigma x is the standard deviation for the x data set. Similarly, for the y value for the point 1, we can also calculate z y value for the first point, and we use y1 minus mu y divided by sigma y. So this is for the first point. And for the second point, we can do this for the second point. So second point is z x2 equals x2 minus mu x over sigma x, and z y2 equals y2 minus mu y over sigma y, and we have this. And we can do all these z-score calculations for all the points. Once we finish the z-score calculations, we multiply for the first point the x z-score and the y z-score. Multiply these two together, and we get one product. And then we calculate the product for this point, and we calculate the product for all the points. Then we sum up all these z-score values. So z x1 times z y1, then plus z x2 times z y2. So we write this one as I and I. Then we add all this together. Then we divide it by the total number of data set minus 1, which is the degree of freedom. So we divide it by n minus 1 here. And we call this as the correlation coefficient. And we can write all this we summarize all this with a formula, which is here. So the R is called the correlation coefficient. R equals, this point, the summation is for R equals 1 to n. When R equals 1, that is x1 minus the x bar, which is the mean of the x data set, then divided by sigma x, then times y1 minus y bar, then divided by sigma y. Then these two multiply together. So this is z score for x1, this is z score for y1, multiply together. So this is for the product for the first point. Then when I equals 2, we do this x2 minus x bar over sigma x, then times this the second product. Then we calculate the sum of all this product, add up together, then divided by the total number n minus 1. So this is called the correlation coefficient. In this example, we see this. For this point, and we use this x, this part here, x value is here, minus the mean of x is this value, then divided by the standard deviation sigma x, and this value gives us a negative 1.68. The negative number is because of this value is less than the mean of the x value. So this is negative 1.68. This is the zx1. Similarly for zy1 is use this value in y minus the mean of the y, which is around here, so give us this one. And this value is positive because it's larger than the mean. Positive divided by sigma y, so this is 1.74 is the z-score for the y1. And these two multiply together, so negative 1.68 times 1.74 give us the product. So this one here equals negative 1.68 times 1.74. And we know this value is negative. The reason is because this point is in the second quadrant. Similarly for this point, the product must be negative, negative, all these are negative. And this part here is the z-score for x here is positive, but the z-score for y here is negative. So the product in the fourth quadrant is also negative. But the value of the point here, this is a positive z-score for x, positive z-score for y, and so this product is positive, this is negative, this is negative. And the point in the third quadrant, the z-score for x is negative, the z-score for y is also negative. So negative times negative is positive. So this is also negative, positive. Then we add up all this product together. Looks to us, in this example, we have more negative product, this and this, and we have less number of positive product. So the sum we expect will be a negative number. The negative number then divided by n minus 1, which equals, let me see how many points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, so maybe 23. So the n equals 23, then n minus 1 equals 22. So a negative number divided by 22 still is a negative number in this example. That means the correlation coefficient will be negative. That means if this value, if it's not equal to 0, looks like it's not equal to 0. If not equal to 0, that means x and y are correlated. Because the correlation coefficient is negative, that means it's negatively correlated. The physical meaning for a negative correlation coefficient is the larger the x, the smaller the y. We can see the line, the form may look like this. So the larger the x increases in this direction, and the corresponding y will decreases in this direction. So that's why it's called negative correlated. So this is the concept for correlation coefficient. We have an example to show you how to calculate the correlation coefficient. Right? Suppose we are given a data set. The first point is 1, 2, means x equals 1, y equals 1. Y equals 2. The second point corresponding x equals 2, y equals 5. X 3, y 6, 4, 8, 5, 11, and so on. We have n equals 10 pairs of data. You can plot these 10 pairs of data with the scatter plot, but it's not plotted here. The step 1, we know we need to calculate the z-score for x and the z-score for y. To calculate the z-score, we need to know the mean and the standard deviation of the data set. So the step 1, definitely we need to calculate the mean and the standard deviation for both x and y data set. The mean for x data is x bar equals the sum of all the x values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So add all this together, then divided by n, 10 here, not n minus 1. And this one equals 5.5. Similarly, for the y value, the mean will be 2 plus 5 plus 6 plus 8 and so on all the way to the 20, and then divided by 10 again, and that value equals 11.7. The next one is to calculate the standard deviation. The standard deviation, the definition is standard deviation is the sum, the square root, the number and the square root sign is called the variance. So this is n minus 1, and the sum of n minus 1, and the sum for all i's, xi minus x bar, and then square. So for this example here, for x, we know the mean equals 5.5. So the first data equals 1. So 1 minus 5.5, then square, then plus here, xy minus the x bar, then squared, then plus second point, plus next point, and plus the last one. Right? Last one is 10 minus the mean 5.5, then squared. Add all this together, then divided by n minus 1, which equals 9. Then take the square root. This gives us 3.0277. So this is the standard deviation for the x. Similarly, for y, the standard deviation equals 6.3779. Okay, so this is the step 1. We need to calculate the means for x and y, the standard deviations for x and y. The next step is to calculate the corresponding z-score. So we need to do this point by point. For the first point, zx equals x1, the first value, minus x mean. So this is x, this is x bar, and this is sigma x. So the x minus x bar, x1, minus this, then divide by standard deviation, and this gives us this value. And for the y, same thing, the y1 equals 2, so y minus y bar over sigma y, and this value equals this. Then we need to multiply these two numbers, negative 1.48, multiply this one, and the value equals 2.2 something. Right? And we can see this point actually is in the, because zx is equals negative, and zy is also negative, so it will be on the third quadrant. Right? So like this here, it will be somewhere here. For the second point, we do this, follow the same steps, and this value equals this. So this value is also somewhere in the third quadrant, and we do this point by point until the last one, zx equals this, zy equals this, and both z-scores are positive, and the product is also positive. This value will be somewhere here. The last step is to add all this product together. This one, plus the third one, fourth one, until the last one. the 10th one. Add all this together, then divided by n minus 1. N equals 10, so n minus 1 equals 9. And this gives us a 0.9926. So that means the correlation coefficient equals 99%, 99.26%. So very close to 1. The maximum correlation coefficient equals 1, and the minimum equals 0. So in this case, they are almost perfectly correlated. And we know here, because the sign equals positive, so they are positively related. That means the direction is positive. So if we draw the lines will be in this direction. It's like this. Next, we'll discuss the correlation coefficient properties. The correlation coefficient is a measure of a direction sign, and positive or negative, and the strength. Strength means the absolute value here, of a linear relationship. So this only works for a linear relationship. If the strength is very large, that means correlation coefficient can be equals positive 1 or can be a negative 1. If the correlation coefficient is small, that means it's equal to 0. From the formula we see the correlation coefficient is calculated using the means and the standard deviations of both x and y variables. Correlation can only be used to describe the quantitative variable. So if categorical variables do not have means, we cannot calculate standard deviation also. So we cannot use the correlation coefficient for categorical variables. The correlation coefficient treats x and y symmetrically. It does not distinguish the x value and y values. Look at here. This is the z-score for x. This is the z-score for y. This term is the only term that has x value. This term is the only term that has y value. This is the x times y, zx times zy. If we switch the position on zy, we calculate zy times zx, that doesn't matter. That means if we said this value is x, this value is y, or if we said this value is y, this value is x, it won't change the correlation coefficient. That means the order of x and y doesn't affect the correlation coefficient. So when you calculate the correlation coefficient, you are given two sets of data, x and y. You don't need to care which one is x, which one is y. The correlation coefficient is unitless because this score is unitless. When you calculate this score, you do not give us a unit. For example, equals minus or equals no matter what. The z-score is unitless. The product of these scores is also unitless, so that correlation coefficient is unitless. It's only a number. Because z-score is unitless, that means the x value can be in with 1 unit, the y value can be with a different unit. For example, the x can be in milliliter, and the y can be in, for example, temperature, in degrees. That doesn't matter because for all the degrees we can calculate the z-score, and for all the millimeters we can calculate also z-scores. Then we just multiply these z-scores together, then add up, then divided by n minus 1. So that's how we calculate the correlation coefficient. So correlation coefficient can compare two data sets with different measured in different unit or variables, or even totally different. Again, when we calculate correlation coefficient, we know we need to use mean, we need to use a standard deviation. Both the mean and the standard deviation are not resistant to outliers. If we have an outlier, the mean may change significantly, the standard deviation may change significantly. That means the correlation coefficient is not resistant to outliers. As we said, the range of correlation coefficient can be, the maximum can be 1 or -1 with different signs, and the minimum can be equal to 0. In this example, the scatter plot showed if we draw like this part is the mean of x, this one here is the mean of y, then we can see this product is negative, this product is positive, this product positive, this negative, negative here. Then it add up together, looks like the sum may equal to 0. That means all these data sets are randomly distributed in this 4 quadrant. So that's correlation coefficient R equal to 0. That means this x and y are not correlated. There's no relationship between these two. You cannot see this is positive or negative. And for this one here, if we draw the trend, the form, it looks like linear and positive. Right? Again, if you calculate the correlation coefficient, looks like those are positive, positive, negative, negative. Look like we have more positive product than negative product. So the sum will be positive, and the positive may not close to 1. And actually, in this example, the R equals 0.5. We claim that X and Y values in this example are correlated, are positively correlated, but the correlation is not that strong. In this case, the correlation coefficient is only 50%. In the next example here, and the form still linear, and the direction is positive, and if we calculate this, we have much more positive here, 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 and we have much less negative in the 4th and the 2nd quadrant. So we can expect the sum of all this z-score product will be very positive, and divided by n-1, they are very close to 1. Actually, in this example, that's equals 0.9. And the conclusion is x value and y value here, in this example, are strongly correlated, and they have a positive relationship. That means the larger the x here, the larger the y. And this example, we can guess from here, based on our understanding in the first 3 examples, there looks like there's a correlation, and if we say the correlation, maybe it looks like this way, and so we know the correlation coefficient must be negative, and the calculation says yes, it is negative, and we claim the correlation is not that strong. Why is not that strong? Because all these points are closed, are loosely, and not that on this very close to this straight line. So the correlation coefficient actually equals just 30%, negative 30%. This one is stronger than this, still negative correlated, is closer to the straight line. And actually, the correlation coefficient is negative. Negative means like this, negative here. Negative relationship means the slope of the line is negative. So this is negative here, it's negative here. And this is 0.7 is much larger than 0.3. That means they are much more compact in terms of much more closer to the straight line. And this one here is even is the strongest. And again, it's negative like this way compared to this positive, and the 0 there. And the correlation coefficient is very large because very close to -1. So it's the strongest.